In our last lecture, we learned that many properties of enantiomers are identical to one another, such as boiling and melting point. So how do we distinguish these two enantiomers from one another? The primary method that scientists have developed for this purpose is to measure the rotation of plane polarized light. The experiment is set up in a polarimeter as follows. Light is passed through a grating to create plane polarized light. Plane polarized light has a certain vector direction. A chiral compound in a sample will cause a rotation of that vector from its original orientation to a different orientation, and we can detect that orientation with a detector. Two enantiomers can be distinguished from one another because they rotate the plane polarized light by an equal amount but in opposite directions. If we have rotation of the plane polarized light in a clockwise manner, as indicated above box B, we call this the dextrorotatory isomer. You may notice a small d or a plus sign in front of some compounds to indicate to the reader that they are dextrorotatory. If, on the other hand, the plane polarized light is rotated by the sample in a counterclockwise direction, this is the levorotatory isomer, and you may see a small L or a minus sign in front of it. If a sample does not rotate the plane polarized light at all, the sample may simply be an achiral molecule, or it could be a 50-50 mix of enantiomers whose rotation of the plane polarized light cancel one another out. Because of how enantiomers are differentiated, we have some vocabulary to learn associated with this. For example, a sample is called optically inactive if it does not rotate plane polarized light. A compound that is optically pure has no side products and has achieved the maximum rotation of the plane polarized light. This would indicate that only one enantiomer is present. If an equal amount of both enantiomers are present, this is what is called a racemic mixture. This, as we mentioned on the previous page, would be optically inactive because the rotation of each enantiomer would cancel. It is often important to be able to assess the optical purity of a compound. This is most often done in terms of what is known as an enantiomeric excess, sometimes abbreviated EE. This equation shows why it is called the enantiomeric excess. At the top we have a quantity expressed as concentrations, showing how much excess concentration of the more abundant enantiomer A there is in your sample compared to enantiomer B, over the sum of both concentrations. Although not a focus in this class, you will also see an expression of optical rotation expressed by this equation. The take-home lesson from this equation is that both the concentration and the length of path of the sample holder through which the light passes will of course have an influence on how much the light is rotated by the sample. There's also some influence of the temperature as well as the wavelength of the light used. Given the importance of being able to determine the concentrations of different enantiomers, we obviously need a convention to designate the absolute configuration of molecule in the name. These two molecules are identical in terms of their constitution, however, the configurations are different. We use the prefixes R and S, R standing for rectus and S standing for sinister. We would name these molecules R2-butanol and S2-butanol. The configuration in terms of the R and S label depend only on the shape of the molecule, and it is not determined by the optical rotation. Therefore, the R isomer is not necessarily the dextrorotatory, not necessarily the levorotatory isomer. Could be either one. It only has to do with the relative orientation of the different groups coming off of the chiral atom. In order to apply and learn how to use these R and S labels, we first need a system which will allow us to prioritize the different groups coming off of the chiral atoms. The first thing we check for is the atom directly attached to the chiral atom. When we compare A to B to C to D, for example, we prioritize them first in terms of the higher atomic number of that atom. The higher atomic number is a higher priority. Sometimes these will tie. In cases where this atomic number ties, the higher mass has the higher priority. For example, deuterium, which weighs 2, would have a higher priority than a proton, which weighs 1. We may further have a case where both A and B are the same exact atom. Let's say they're both carbon. If and only if you encounter such a tie, you compare the highest atomic number group on atom A, and you compare that to the highest atomic number group on atom B. If those tie, you move on to the next highest atomic number, A2 versus B2, for example. If and only if those also tie, then you would move on to comparing A3 to B3. And you move out in that manner, comparing only the highest atomic number atom to the highest atomic number atom on the initial tie site, A1 versus B1, and you move out from there. Let's consider as an example this chiral center in this molecule. If we look at the atomic numbers, we see that the highest atomic number is for fluorine, the lowest atomic number is for the hydrogen, so those would be priorities 1 and 4, but we have a carbon which ties a carbon on those two substituents. We need to take a closer look at those two substituents specifically. I've drawn these out in a little more detail. Because the initial comparison site of carbon to carbon ties, we look for the highest atomic number atom coming off of each of those carbons. In the first case, the highest atomic number is carbon. In the second case, the highest atomic number is also carbon. So comparing those two carbons in squares, they again tie. So we go back to our original tie site and say, well, what is the second highest atomic number? It's another carbon. The second highest atomic number atom coming off of this carbon is going to be a hydrogen. You only have one carbon and you've got two hydrogens. Now, this carbon beats this hydrogen. So that entire substituent, going back to our original structure, outranks this other substituent in terms of priority. Things become more complicated if a substituent coming off of a chiral site, let's say this R was a chiral atom and we were looking at the substituent, if those substituents themselves have multiple bonds. The convention that we've developed is to get rid of the double bond just for the purpose of prioritizing. This has nothing to do with real chemistry. And drawing in fake atoms. So instead of having a carbon-carbon double bond as shown on the left, we would change to pretending that there are additional carbon atoms there. So if you look at this convention, this carbon is bound to one carbon, two carbons. This carbon has 1, 2 bonds to carbon. So it's really just for counting how many bonds to carbon there are, and not forgetting that you have 2 bonds to carbon instead of 1. Let's consider this alkyne. Instead of drawing 2 extra bonds in addition to this first one, we will draw some dummy atoms in. And I've circled those dummy atoms to indicate those are not real atoms attached to the structure, but it's to highlight the fact that each of these 2 carbons in the squares now has 3 bonds to the carbon, just as it had 3 bonds to the carbon over in the original structure. The same premise applies if you have a nitrogen. This carbon on the left has 3 bonds to nitrogen. We leave one of them in. We draw 2 more, so you've got 3 total. And those are now the circled dummy nitrogens. Now the nitrogen on the right started off with 3 bonds to carbon. We only have 1 now, so we have to put in the other 2 bonds it had to carbon to these fake constructed carbons to make it easier to count. Next, once we have applied these rules for prioritizing, we want to tilt our structure, reorient it in some way, such that the lowest priority group points away from us. Now the lowest priority is the 4th priority substituent. If we, for example, tilt this structure so that the H is pointed away from us, we have the OH, the ethyl group, and the methyl group, priorities 1, 2, and 3 towards us. This is sort of like a Newman projection where the group behind the front 3 is hidden by that circle. And our convention is to count from priority 1 to priority 2 to priority 3. If in drawing the arc from 1 to 2 to 3, when the lowest priority substituent, the 4th priority, is behind the structure, away from the viewer, if that goes in a clockwise fashion, 1 to 2 to 3, we use the R prefix to designate that configuration. The nomenclature rules otherwise remain unchanged from what we'd learned previously, so this is R2-butanol. If you process in a counterclockwise fashion when you count from the 1st to the 2nd to the 3rd priority substituent, this requires the S designator of configuration, so the molecule at the bottom here would be called S2-butanol. Often it's this reorientation of the molecule, requiring a certain group to be pointed away from us, that causes students trouble to manipulate a drawing on a piece of paper that is supposed to represent a 3D shape. Generally, the most familiar item that has handedness in regular life is a person. Many of us, if we look at this person doing push-ups, we know that this person has a right hand and a left hand, and we can tell which hand is the right hand and which is the left hand, regardless of which way the person is facing, just because of our experience interacting with people in our regular life. So remembering that this type of hashed line indicates that this arm is pointed away from the viewer. This arm away from us would be the chiral athlete's right hand, and this would be the chiral athlete's left hand. This would be the chiral athlete's feet, and this would be the chiral athlete's head. If I draw, instead of a face and hands and feet, on this same tetrahedral scaffold, you see this scaffold is identical to the elegantly drawn stick figure body of this athlete. We can then learn how to reorient this molecule in the same way as we would redrawing this person facing a different direction. In this case, instead of a head, I've drawn an OH group. Instead of feet, I've drawn a CH3 group. Instead of a right hand, I've drawn an H. Instead of a left hand, I've drawn an ethyl group. If I asked you to take this molecule and reorient it so the H was pointed towards us, that might be a more difficult task than if I said, please redraw this chiral athlete doing push-ups but facing the other direction. But they're really the same problem. You're just identifying which groups on the person represent which groups in the molecule. So if this athlete is doing push-ups and I draw him so that his right hand, which is in the position of the hydrogen away from us in the top drawing, if I want that group pointed towards us, I draw the right hand, which looks different from the left hand because I've drawn this nice tattoo on his hand, and I simply put the head where the head would be on this person, the feet where his feet would be, and the left hand where the left hand would be. I can also draw the molecule in that way. So I imagine in my head, well, what was the head? It was the OH group. What was the right hand? It was the hydrogen. And now this right hand is forward. The left hand was the ethyl group, and the feet were the methyl group. And this way I can reorient so that whichever group I want is pointed towards or away from me. Now, tetrahedra for molecules can be drawn in a variety of different ways. And it's not always a very easy task to convert this to the push-up drawing that I drew on the previous page. But you can always reorient your page. If you're doing a paper exam, you can rotate your head and look at the computer screen a different way. You can simply imagine an athlete doing different tasks, such as a handstand or a push-up on the ceiling. And as long as you assign for the person, what's the head, what's the feet, what are the hands, and you reorient your molecule in the same way, saying, okay, this is my head, it's the highest priority, this is the left hand, this is the feet, this is the right hand, and I fill in my priorities, I can then reorient my molecule or my human being in any way that I wish. And there are a variety of other ways and tricks that one can learn to reorient chiral molecules. The point is this is going to be a very important task to be able to complete in this class. You can use model kits. You can build a model and rotate that and look at the physical object in your hand. But you have to find some way that works for you to accomplish reorienting the molecule. It's also very important to point out that there are many ways, many orientations of the same molecule that one can draw on a piece of paper. If you had a model kit and you built a molecule, you could rotate it, turn it upside down, rotate it again, and you could look at it from a variety of different angles. You can draw each of those different angles on a piece of paper with the wedge and hash line representation. And on this page I try to emphasize that by showing 12 different ways that I can draw the exact same molecule. A good exercise would be for you to attempt to convince yourself that all of these are the same molecule. And if you want to pause this video, you can try to figure out the other ways that you can fill in the substituents, where I've put the ethyl group at the top in these two cases, or a hydrogen at the top in these two cases. And you've got to keep the molecule the same, in the same configuration. One strategy that people sometimes use is to focus on one group. If I have the OH group, for example, I can focus on how it moves. So here I'm saying we've got to keep the ethyl group at the top. So if I imagine holding my model kit by this group and just rotating it in this direction, my OH would move to where the H is, and I've drawn that there. If I kept spinning this, the OH would rotate to this position. Now where was the H with respect to the OH group? Well, the H started here. If I'm going to rotate in this direction by one spot, the H would end up here. If I rotate my molecule again to look at it from a different angle, it would rotate to this position. And then it's just a matter of filling in the CH3. And now I have two additional ways to represent this molecule. These molecules, again, I want to emphasize, all these representations here beside box A represent the same molecule, just rotated, reoriented, as I showed in the first row. All the molecules in this whole slide are S2-butanol. I used the same strategy for this row that I've already filled in. I moved the OH first over to this spot, then I rotated again to this back position, and so on, and redrew the other substituents in the same positions, leaving the CH3 at the top in this case. And then I could switch from the OH to the ethyl to the methyl, the H being at the top of the structure, and again just fill in the substituents. Rotating the OH to the front position here, rotating it to the back position here, then beside the OH is the CH3, and then of course the ethyl group to fill out the rest of the substituents. So all 12 of the structures on this entire slide are just looking at the molecule S2-butanol from different angles. Now drawing wedges and hash lines can sometimes be cumbersome, and those symbols aren't available in all word processing programs, and certainly they weren't available to early chemists who wrote their papers and textbooks using a typewriter. So Fischer developed a Fischer projection where you can show the three-dimensional shape using ordinary straight lines that don't have a wedge or hash appearance to them. In the Fischer projection convention, the horizontal lines will always represent groups coming towards the viewer. So the Fischer projection will look like this. It will have straight lines, ordinary lines, not wedges or hashes. The horizontal groups come towards you. So I show you that the Fischer projection, by definition, has these horizontal groups coming towards you as if they were drawn on wedges. The vertical lines, on the other hand, will always represent groups going away from the viewer off the central atom. So you generally draw a Fischer projection, as I have here, where the chiral atom is at the center and the four groups are drawn coming off of it. So when you see this, by definition it equals this structure. It's important to be able to draw Fischer projections and interconvert between those and our traditional wedge and hash line structure we've seen so far. If we continue with our analogy of thinking of the more familiar handedness of humans, and we think of a Fischer projection as horizontal lines coming towards us as if someone's coming in to grab you or give you a hug, this would be this individual's right hand, and this would be the individual's left hand. This would be the head, and this would be the feet. All I have to do is redraw that human being in a push-up position where I designate which hand is the right hand, which hand is the left hand, which are the feet, and what is the head. And if I look at the Fischer projection and compare that to the wedge and hash line structure, I can correlate the priorities of the actual chemical pieces with the positions where position 1, 3, 2, and priority 4 are in the Fischer projection. 1, 4, 2, 3. So if I redraw this individual doing push-ups, I would say, well, this is the first priority. The feet in this case are the third priority based on what chemical groups they represent. The right hand is the fourth priority and the left hand is the second priority. Then when I draw my scaffold with the wedges and hash lines to accomplish the same molecular orientation, I would have to place my first priority substituent here, my third priority substituent here, my fourth priority substituent here, and my second priority substituent here. The Fischer projection also makes it very easy to designate a configuration. If my Fischer projection represents, by definition, this type of structure, and my rules for assigning an R or S label say you've got to put your fourth priority substituent away from the viewer, and then you need to draw arrows, an arc from 1 to 2 to 3. Well, in the Fischer projection, a vertical group is already away from us. In this case, we have a clockwise procession from 1 to 2 to 3, so we have an example of R2 butanol. The next part of this slide says, well, what if I'm asked to convert this Fischer projection at the top to a wedge and dash structure? There are several ways you could draw it. Again, I showed you 12 ways to represent a molecule on a previous slide, so there are many ways you could do this. And here is one way to do it. Just to make my drawing simpler, instead of drawing out the whole groups, I just wrote the priorities, because that is what's important for being able to assign the R and S labels. Next, I'm going to say, well, if this was a person standing up, trying to hug you with the arms horizontally towards you, what would this look like? Well, if this person is facing me, the right hand is priority 3 based on its orientation with respect to the actual molecule. Left hand is 1, feet 2, head 4. If I'm trying to convert this to a wedge and dashed structure, I would like to show it in a normal tetrahedral geometry as we're used to seeing, like this. Now I can imagine that's a person doing push-ups where this is the right hand and this is the left hand. If I do that and I fill in the molecular groups that have that handedness, my left group is priority 1. If I go back to my original structure to see what I need to put there, that's an OH. The head position priority 4 is an H. The right hand is priority 3. Looking at my original drawing, that was the methyl group. And then feet would have to be the ethyl group. So this is a way to convert the handedness of a molecule using our familiarity with the handedness of a person. Now what if we're asked to go the other way? What if we're given the name and asked to draw the structure? So R3-methylheptane. Let's consider that structure. So I start off by drawing 3-methylheptane. I identify the chiral center. And now I'm going to identify what the 4 groups are coming off of that carbon. There's a hydrogen, there's a methyl group, there's an ethyl group, and then there's this chain which has 1, 2, 3, 4 carbons, so there's a butyl group. So I'm going to simplify this. Because the focus is on the chiral atom, I just need to know what the substituents are. And now I'm going to simplify this even more by simply writing the priorities of these groups and redrawing this. If I want to draw a Fischer projection for this species and make sure that it's an R isomer, I'll want to position my lowest priority group, in this case it's hydrogen, in the back. The vertical lines represent groups going away from us, so that will place the hydrogen there. If I want to make sure that I have the R isomer, I need my arc from 1 to 2 to 3 to go in a clockwise fashion. Now that I've drawn that in and positioned the 1 and 2 and 3 where I want them, I can fill in the specific groups. C4H9 for position 1, ethyl group for position 2, and methyl for position 3. If I then want to convert this to a wedge and hash line structure, I could use the same process as I did up here. Now some people can see the three-dimensional shape of objects without having to manipulate the shape using familiarity with people, and that's fine as well. If I went through the same process, head, feet, right hand, left hand, I would then have another way to draw R3-methylheptane. And again, there are 12 different ways at least you could draw this based on the previous pages. Whatever you find works for you to draw this, this is one method. In addition to enantiomers, there are compounds called diastereomers. Diastereomers are not the same as one another. So like enantiomers, they are non-superimposable. But they're not mirror images of each other. They're stereoisomers, they're not mirror images, and they're not the same. In the context of the current lesson, these are generally compounds that have more than one chiral center. if a compound has n chiral centers, and each of those has two potential configurations, R or S, you have up to 2 to the n power stereoisomers. So let's compare these 4 compounds, which have the same constitution, but they're stereoisomers. You have the same groups coming off of the top carbon, methyl, chloro, H. In all these cases, same groups coming off the bottom carbon. They're both chiral centers in each molecule, top and bottom carbons. And we have to figure out what's the relationship between these compounds. We can see visually that 1 and 2 are mirror images. So 1 and 2 are enantiomers of one another. Likewise, 3 and 4 are mirror images of each other. Cl reflects to Cl, H reflects to H, etc. So 3 and 4 are enantiomers as well. But what about the other pairs? How does 2 compare to 3, for example? The top carbon looks like it's a mirror image of the other top carbon, but the bottom's not the mirror image. So they're not the same. You've switched on the top, that the H is on the left compared to the right from 3 to 2. But you didn't switch the configuration of the bottom. The OH is still on the left, the H is still on the right. So those aren't enantiomers, but they're also not the same. That's a case where you have diastereomers. So any pair that does not have a relationship of enantiomeric to one another, those are cases of diastereomeric pairs. The final topic I'd like to cover in today's lecture is the topic of a subset of compounds with chiral centers that are called mesocompounds. One thing we know about compounds is that they can't have a plane of symmetry and be chiral. So what happens when a compound has, like compound 1, 2 chiral carbons, but the way they're set up leads to a plane of symmetry between them? Well, this is exactly what a mesocompound is. A mesocompound is a compound that has chiral atoms in its structure, but the entire molecule is achiral because it has a plane of symmetry. Compound 1 and compound 2 are achiral, and they're actually identical to one another. One is just flipped over with respect to the other. You see, compounds 3 and 4 lack a plane of symmetry, and they have the chiral atoms, and they're mirror images of one another. So 3 and 4 are enantiomers of one another, and they're chiral compounds. And any other pair of compounds, let's say 2 and 3, are diastereomers, because whereas one of the chiral sites, is identical, the other one's been switched. In this case, the bottom is the same in both cases, but we switched the H from the right to the left and going from 2 to 3. So any other pair that you look at, you'll find that they're not mirror images and they're not identical. Those are diastereomers.